Hello and welcome back. In this video, we'll focus a bit on explainable AI, in particular in conjunction with image models in PyTorch. The modern deep learning frameworks and the modern image networks have achieved remarkable successes, and they have become more complex with time, and it becomes more and more difficult to understand what these models actually do, and it becomes more or less impossible to understand just from the model itself how a model arrives at a certain prediction, and this is why they're called black box models. Generally, we have two ways of improving the interpretability of machine learning models. Either we build a white box model, these are then interpreted as such, but this is very difficult, for example, for image classification. Or we use so-called post hoc methods. This means we take an existing classifier, for example, for image classification, and then use another model around it that tries to determine how in particular this model arrives at a interpretation and assignment of this class. In this example, we use the Lime package as a post hoc explainer for a black box model. So that means we use a standard image classification model, in our case Inception version 3, and then use the Lime package to generate explanations for a specific image to understand in more detail how the model arrived at this assignment. Because there are a number of setups to take, we will split this video in two parts. We'll first focus on all the setups, and then in the next video we'll go over to actually using the Lime package. In this example, we use the dataset cats versus dogs, which you can find at Microsoft and download it from there. A few sample images are part of this repository, but you can explore more, of course. You download the files and unzip it if you like. And the Inception model was trained on the ImageNet dataset. This is a large dataset of millions of images, and that consists of 1,000 classes of various objects, and in particular also cats and dogs. Now we need to understand, if we want to use these classes, how the index of a class is related to the class label in human readable form, and we have to sort of get access to the mapping. You can find one, for example, at Google, and download this from this URL. This is a JSON file and essentially contains a dictionary of what each class means for the computer and for us as humans. So we start by importing our standard libraries, Torch, Torch Vision, and Torch Vision gives us access to the Inception version 3 model with the weights. For plotting, we need JSON to open and interpret the JSON file with the class assignments. We need this library to display images, and here are the crucial two libraries that we need. Lime is the package that creates the image explanation, and we use a convenience function mark boundaries from cycled image that we can then use to overlay the regions the network thinks are important for the specific assignment. Now let's start with the setups. The simple part is to instantiate an instance of the Inception model. We can use the Torch Vision convenience function for this, and we use the default weights. So once we run this, PyTorch will download the model and the weights for us and gives us access to this model. As we said before, the ImageNet data is 1,000 classes and millions of images, and we have this JSON file we have downloaded earlier to tell us what each class assignment means. And to be able to do this in human readable form, we need to load this JSON file and essentially have an assignment of the class index, and also here the numerical representation of it with a human readable form. So we do this here and write ourselves a little convenience array or a list in Python, where we open the file and load it into the JSON library, and then we extract the mapping between image class and the human readable form, and let's just print a few examples. So at the end, this list then contains the human readable labels of the specific class. Next, we need to be able to access the image that we want to analyze properly, and in particular, we need to expect later for Lime that the image is in RGB format, so we make doubly sure that it is, even if it's in RGB format already, then the double conversion, so to say, will not do any harm. So we write ourselves a little convenience function load image, where we open the file in binary mode for reading, use the PIL library in Python to open the image and interpret it, and also convert it to RGB. And as we said before, if it's already in RGB format, it doesn't really hurt. So we do this for an example and show the image of a dog. Now, because the inception network also requires that the image has specific properties for training, we need to make sure that we reproduce this for our images. In particular, we need to bring the image to the right dimensions, convert them to a tensor, and normalize it according to the ImageNet recipe. For the inception network, this one expects the images to be of 299 by 299 pixel, and it expects it to be normalized with these numbers. So this is what we need to do when we want to pass this image to our model. Because we use the Lime package later, we split this into two convenience functions: a general resizing that can also be applied to any NumPy style representation that is expected by Lime, and the part that is specific to PyTorch in the inception model, the normalization. So first we do the resizing and center cropping so that we make sure that we have exactly the same shape of the image, and then here the normalization with those two arrays to make sure that the image values are what is expected from the training of the inception. Now we need to do the next setup. The scikit-learn library has established itself as a sort of de facto standard in many machine learning applications. In particular, its style of model fit, model predict, model transform, and model predict prober. And this is what the Lime package also expects. It expects this kinds of interface. Unfortunately, however, standard PyTorch doesn't quite adhere to this convention, so we need to implement the corresponding functionality ourselves. In particular, for the later use, we need to get a model that predicts in the same style as predict prober would in scikit-learn. Also, a model in PyTorch always assumes that we have images that are passed in batches, because we would normally train the model or get predictions in batches of images. However, here in our example, we only want to pass a single image, like the boxer we have shown above, and want to get an explanation for the single image. So therefore, we need to convert the single image into a batch format so we can feed it into the model. Furthermore, the PyTorch model expects the image data in tensor format, and, confusingly, Lime expects it to be in NumPy format. Of course, NumPy is like the base standard, since Lime itself is not related to PyTorch or TensorFlow or any other package, so we need a common data format. So this makes sense to use NumPy here, but unfortunately for us, this means that we need to be able to convert between the tensor format of PyTorch and the NumPy format for Lime. And also, when we have our model defined elsewhere, because we cannot pass this as an argument in the methods that we need to develop, so we need to sort of rely on global variables a little bit. And since we move the model to CPUs or GPUs, and Lime doesn't know about those, we need to, again, extract all the numbers and make them available. So long story short, we need to mimic the behavior of predict prober, and where we let the model predict the output of a single image for the classes, and then we need to convert this using the softmax function into probabilities, or pseudo probabilities rather. And in order to be able to do this, we also need to get away from the tensor implementation, the computational graph PyTorch uses in the background, move them to the CPU and convert them to the NumPy format so that we have in the end just standard numbers that we can use with the Lime package. So long story short, here's the code for it. We define ourselves the predictor or predict prober function, which is called predict here. We can't pass the model as a parameter, so we need to rely that we have it defined elsewhere. We move it into evaluation mode, and here is the magic that transforms a single image into batch format. Then we need to make sure if we have a GPU available or not. Then we move the model to the device, we move the single image that we have converted to a batch to that device, and then run the model on this batch and get the outputs for the classes and use the softmax function to convert this into the pseudo probabilities. These are the ones we want to return for the use in Lime. But in order to be able to get to the number, we need to sort of undo everything that is related to PyTorch. So we need to detach it, move it to the CPU, and convert it back into the NumPy format. You can see we can chain these operations together. Now that we've done this, we can do a test prediction. We take our image that we have loaded up earlier and run this with our new convenience function, and we can indeed see that this is a box. So in the next video, we'll follow a bit more closely how we can use this to generate a local explanation